Hi, this is Dr. John Bergduff. This is going to be a video on three-dimensional geometry. And in this video, we're going to explore the concept of a polyhedron, a net, and then we're going to introduce Euler's formula. I'm going to switch cameras so I can show you some notes. So here we have a definition that I want to show you. A polyhedron is a three-dimensional object consisting of several polygons joined at their edges, fully enclosing a single hollow region with no holes. We're going to see an example of this in just a minute, and we'll come back to this definition so that you can see exactly how it works. But it's a three-dimensional object consisting of several polygons joined at their edges, fully enclosing a single hollow region with no holes. Now, we're also going to define something called a net. A net is a two-dimensional representation consisting of joined polygons, which, when cut out along the outer edges and folded up, creates a polyhedron. Basically, it's a two-dimensional representation of a three-dimensional object. Let me show you an example. This is a net. As you can see, it's a three-dimensional object. What I would do with my net is, if I can imagine using my scissors and cutting along the edges, the outer edges of this net, and this is going to be like in the cooking shows. Rather than going through each step, I'm going to show you each step as we go, sort of the finished product. If I cut out around the edges, I'll get this figure folding along the inner edges. So just imagine folding along those edges like this, 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 and this, and folding it up beautifully. I think you can begin to see a three-dimensional shape developing. Carefully tape around those edges. And again, like in the cooking shows, we put that in the oven and bring this out right here. This is my polyhedron. And you can see how the net has formed a three-dimensional objects. The polyhedron, again, is a figure, a three-dimensional figure whose faces are polygons. They're joined at the edges. This fully encloses a hollow region. The hollow region's on the inside, and there's no holes in it anywhere. So that's a polyhedron. Now, in this polyhedron, we've already kind of used one word. The polygons that form the sides are called the faces. We're going to count how many there are in just a minute. The edges are where the polygons join together to create the three-dimensional object, and the vertices represent the points where these edges ultimately meet. Let's count. I've got a little table here that we're going to fill out. And as we do this, we'll count them. So we're going to count the number of faces, first of all. This object, by the way, is called a rectangular pyramid. Looks like the pyramids in Egypt. And the faces consist of four triangles, sorry. 1, 2, 3, 4. 4 triangles plus a rectangle that forms the base, so to speak. That makes a total of 1, 2, 3, 4, 5 faces. So let me write that into my chart here. The vertices, again, are the points. Let's count those. If we start with the square on the bottom, we can see that there would be 4 vertices corresponding to the four corners of that rectangle. And then there'd be one additional vertex, the one right at the top, what we might call the apex of the pyramid. And that makes a total of 5 vertices. 5 faces, 5 vertices. Finally, the number of edges, a little bit harder to count sometimes, but the edges are the line segments where the polygons meet. As you can see, if I look down from the vertex, there's 1, 2, 3, 4 edges there. And then turning it over and looking at the base, the rectangle, the 4 sides of the rectangle make 4 additional edges. So that's 1, 2, 3, 4, 5, 6, 7, 8 edges. 5 faces, 5 vertices, 8 edges. Now, there's a formula that relates those numbers of faces, vertices, and edges in a polyhedron. This is true for any polyhedron. And it was developed by a mathematician by the name of Leonhard Euler in the 1700s. He's from Switzerland, so his name is German. We Americans would look at that word and think, oh, Euler, that's Euler. But actually, that's Euler is the correct way to pronounce that. Euler's formula for polyhedra. This is true of any polyhedron. If F, V, and E denote respectively the number of faces, vertices, and edges in a polyhedron, then the following relationship always holds. The number of faces plus the number of vertices is always equal to the number of edges plus 2. Let's see if that's so in this case. In our case, the number of faces is 5, so that's F. The number of vertices is also 5, that's V. And the number of edges is 8. 5 plus 5 is 10, which is equal to 8 plus 2. And you can check this on other polyhedra as well, but this is just to introduce the concept. And I hope this has been very helpful and that you've enjoyed this video. Thank you very much.